Hydrate, hemiacetal, acetal, or none of the above. Okay, so what you guys should have been able to go through and do is to be able to label these. The first one is acetal,
None.
hydrate, acetal, hemiacetal, and none of the above. Okay. In trying to find your acetals or hemiacetals, so for that matter, I'm going to delete the none of the above because I don't really care about it, is we're trying to find a carbon that is bonded to two oxygens. So if we go through and take a look through all of these, we have that characteristic. Carbon bonded out to two oxygens. If that oxygen continues out to a carbon, we now have the potential for an acetal, but it needs to go out to two carbons on each side. So we'll call that one A. The other one, or the last one, went out to a hydrogen. Because it went out to a hydrogen, we're now looking at a hemiacetal. Okay? And then this one's a hydrate, because instead of going out to any carbons, we went out to hydrogens on both sides. Okay? And the middle one, or the first one, carbons. Recognize that? Questions about finding those and identifying them? Okay. The next part would be trying to identify the species that made them. So let's take a look at those two. What are the species, so the carbonyl and the alcohols that made those? How should we go through and do it?
Rate the bonds.
So the easiest approach is just to go through and recognize that your most polar bond is with the oxygen. So we could just break those. Okay, so there's the first one, broken. I will replace it with a carbonyl. The other oxygens were alcohols. There we go. That was the starting components for my acetal. Make sense? Okay, so I needed 3 pieces to make that acetal. How many pieces do I need to make the second acetal? Step 1 was what? Delete the carbon-oxygen bonds. Replace them with a carbonyl. Make them alcohols. How many starting materials did I use? 1. This one was a cyclic molecule. Okay, we had an intramolecular reaction. The ACS definitely likes intramolecular reactions. Okay, because most students lose track of that cyclic aspect behind it and can't piece it together. So if you are suspicious of a cyclic system, it can be helpful to count your carbons and actually label them out. That was a dumb way to label it, so let's try that again. Actually, I changed my mind. So I've got a 5-carbon chain, 1, 2, 3, 4, 5. At carbon 5, I have a carbonyl. At carbon 1 in this sequence, OH. Anybody have a problem with me calling it carbon 5 a carbonyl?
Yes.
Why?
Because your nomenclature says that has to be your first carbon.
Nomenclature says the carbonyls are higher priority. It should be carbon number 1. The system that we use to number here, it's nothing to do with nomenclature. This is a personal track record. We don't care about that nomenclature, that numbering system, for nomenclature's sake. We care about it to make sure that we don't lose carbons through the process of this. Okay? So don't spend a whole lot of time trying to be like, well, that one's not, which one should be carbon number? That's irrelevant. Okay? Just mark the carbon so that you can identify them. Notice, where's carbon 6? It's connected to carbon 4. So I go to carbon 4, and now I can draw on 6. There's 7. There's 8. there's an OH. Okay? This way I've accounted for all of the carbons, right? And I've potentially reorganized this in a fashion that might make a little bit more sense for an ACS question, because this is now formatted a little bit more linearly, so it would fit nicely within that multiple choice box. Okay? And by organizing it in that fashion, I've also made it a lot more difficult for someone that just knows how to delete the carbon-oxygen bond to reverse the process of the acetal. I've made that a little bit more difficult for them, because now they have to recognize the three-dimensional rotations. Kind of make sense? Okay, so you got a little bit of a cheat for a shortcut to reverse your process, and you've also been told to watch out for straightening those chains. Okay? We had two more acetals that we could look at. Okay, we could again run the process in reverse. We erase those bonds. Yes, I'm attempting to erase them poorly. Okay. So we start with hexanone and the dialcohol, okay, or a diol. Last one, extra tricky, because that one folds up on itself. Okay. Could fold out pretty nicely as a straight chain. Kind of makes sense? Okay. We'll throw this out there just as kind of salt in the wound, potentially. One of the complaints that we often get as teachers is you got to make it real, you got to make it real. Okay, here it's real. Those are all acetals. And usually the response we get is, don't make it that real. Okay. We can either show its direct relevance and you see the undue complications behind it, or we simplify it down so you can see the bare functionality behind it. Okay? All of these have acetals within them. Okay? These are all basic carbohydrates found in biology. We can start with sucrose up at the top. Where is the acetalic carbon? So where's the carbon? The acetal is located in sucrose. Okay. Brave volunteer, circle the acetalic carbon for me. Thank you. Is he right? He's half right. What do you mean he's half right? Carbohydrate, there's two carbohydrates here. Both of them have acetalic type positions. I did color them differently for a couple reasons. The red one is officially an acetal. We've got the oxygen going out. Whoops. Oh, yeah, we'll address that later. That is then connected up with the carbon. The blue one, if we go out, we've got our oxygen that goes out, connected to that same carbon. And then we have the other oxygen that goes out to hydrogen. So that one's not an acetal, that one's a hemiacetal. Okay? Everybody recognize that? Yeah. What's up? So, and I intentionally was kind of vague in the question. So, okay. We should be identifying any point that could be, I said acetalic, and the acetalic is kind of referencing both hemi and full acetals. Okay. Anybody have a problem with the little bend that I'm showing in green there?
I was curious about carbon there.
Shouldn't that be another carbon? It's a point, right? Every point ends in a carbon. Yeah, welcome to biology. Okay. They don't like the orientation, so they just made up some directionalities behind it. Those are not carbons. Those are bonds that they're trying to show goofy. Why? Because they want to, and they can then make up rules. welcome to biology. Okay? Typically what you'll see people do to kind of minimize that confusion, instead of showing them as right angles, you'll see them as a rounded, because then it's not officially a point. Okay? Why? It again goes to how they're trying to draw the structure. They're trying to draw the carbohydrates in a particular fashion, and they don't want to change the orientation. Why not?
Because they're biologists.
Everybody has a hard time with three-dimensional manipulations. If you change the orientation of those molecules, it makes identifying each of the chiral atoms that much more difficult to track. Okay? So the reason they're locking it in that formation isn't because that's what happens in a biological system. A biological system is going to do what OChem does and constantly spin, flip, and rotate and into the lowest energy conformation. Okay? But that is sometimes not easy to see. So biochemists, you notice I added the chemist there at the end, will force the drawing in such a fashion to simplify our outlook on it. Okay? If we go through and look at the rest of these all have that same kind of characteristics. These become a lot harder to track the acetal carbons for. Why? Or carbohydrates in general. Why?
There's a lot of oxygen on there.
There's oxygens freaking everywhere. So you can't just be like, oh, where's an oxygen? Let me evaluate that. Because every carbon has an oxygen. Okay? Which means, yes, that's exactly what you have to do. You have to look at every carbon and be like, are there two oxygens? No. Are there two oxygens? No. Right? And you have to start crossing them off the list. Make sense? Hi. Let's see where my slide... I just need to see where the next slide is. Yep, we're going to double back to that. Okay? So... What's up?
No, we were just saying that one is a hemiacetal.
The big one? This one is a hemiacetal. Where's that hemiacetal found?
In the corner. Yeah.
On the right, top right corner.
Somewhere.
Bad question. Bad question. Let me try that again. Fair enough. Okay. Where is that sugar molecule found in biology?
It's fructose.
It's not fructose, which is extra fun with carbohydrates. It's ribose.
Oh, deoxyribose.
It's not DNA,
RNA.
because what does DNA stand for?
Deoxy.
Deoxy. If you take a look, every single one of those carbons has an oxygen bound to it. So it has not been deoxied.
That's RNA.
To be deoxied, we'd have to remove an oxygen. So this would be found in RNA, ribonucleic acid. To make it deoxy, I haven't taught biochem in a while. This one?
I can't remember if it was L or the 3.
Yeah, that's exactly my problem.
I think it's 3. I can't remember.
Okay. Deoxy, we remove one of those oxygens and replace it with a hydrogen. Which one? I don't remember. It's one of these bottom ones. Okay. And now it's deoxy ribose. Okay. Some people have had biology. Shouldn't you be able to tell me that?
Have you been to
No?
the biology
Okay.
class in the last week? Amazing.
Yes.
They're all essentially like when you start getting the longer chains for they turn into they keep chaining on each other for carbohydrates. So you get like it's a hemiacetal until you snag another one on.
Yes.
And then it becomes an acetal.
So with carbohydrates, we'll continue to link these. For instance, cellulose is a bunch of carbohydrates. Okay? Where else would you store glucose? Fat, okay, is a common place for storing energy. It's also glucose. But aren't cellulose and fat two entirely different systems? Okay, what's the point of fat? To store energy so that you can continue to live, right? Is that what we want cellulose to do?
No.
No, the whole point of cellulose is structure. But it's both glucose. Why so different?
Alpha and beta glucose.
Okay, so we invent a system called alpha and beta glucose. What the hell is that?
It's the orientation is different.
This OH, I think it's this OH again. I didn't quite intend to get this far into it. That OH being down versus up here. Okay, around the acetalic carbon, known in biochemistry as glycosidic. Okay, if you change where that OH is located, you change the functionality of the glucose, and it switches from cellulose structure to fat energy. That's a pretty significant difference. All it's doing is on a simple flip of where the OH is located. Well, how did the OH aim up or down? What is that difference between those two positions? It's literally stereochemistry. One of those is R, one of those is S. Okay? That subtle difference in stereochemistry switches us from structure to energy. That's pretty fascinatingly cool. Okay? Because the basic fundamental building blocks between those two systems are identical except for that one change. That's nuts. Okay? Why do we call it alpha and beta as opposed to R and S?
Biology.
Because it's biologists. Okay? And if we push that a little bit further, not to rip on them too much, why alpha and beta? Okay, well, we discovered one form first. Which form do you think we discovered first?
Energy.
Why energy?
Because it's in sugar. We use it
What's the point of energy?
to be used.
To be used, which means it is reactive. Which means which one are we going to find first? The reactive one. Cellulose is organized in such a fashion that it becomes unreactive. It's harder to find. Which means we went through saying, well, we had these two different things, entirely two different systems. Fat, cellulose. Oh, fat, cool, it's made of sugars. Oh, that's the conformation of sugar. Oh, we don't have to worry about that other one, it doesn't exist. Until we find it exists. Oh, crap, there's two different forms. What should we call those two different forms?
Form A and Form B.
Form A and B. Alpha and beta. Alpha is the energy storage, beta's structure storage. Solely based off of understanding when those things were found. Just kind of neat. Might all be a lie. But it at least makes sense. Okay? So, within that, let's go ahead and split that apart to see what we're talking about. So, if we look at that ribose structure, I think it's mostly true, by the way. If we look at that ribose structure and revert that back to the carbonyl, okay, so first we erase our acetalic bonds. We would draw in our carbonyl, okay, and what do we have? We'd have this OH float off as
H2O.
water. Okay. We have the other oxygen floating off as ROH. Okay. To revert back to the acetal formation, this oxygen has to attack that carbonyl. As it attacks the carbonyl, remember that carbonyl is sp2 hybridized. If that oxygen comes in from the top of the molecule, where does that red oxygen go? Down and away. What if the oxygen comes in from the bottom of the molecule? It goes up. So when we're talking about that glycosidic bond and our difference between our alpha and beta, it's coming back to the fact that addition reactions, we're adding to a pi bond, produce two products because there's two sides where the electrons exist. Okay? Why in biology do we see one over the other form? What's causing that reaction to happen? An enzyme. And an enzyme will physically grab those pieces and put them together because the enzyme is made up of proteins which have chiral atoms. They are all chiral, which means they have a handedness to them, which means when they cause those two to react, They will always react in that exact same configuration. If I want the other configuration, what do I need? A different enzyme. Okay? So that's kind of a neat process. Okay? Next thing I want to address here is that position is what is known as a reducing sugar. Okay? It is a reducing sugar because I can very quickly reduce that position because I have a nice easy carbonyl there. Okay? If we go over and take a look at the sucrose, okay, and in particular the glucose of sucrose, okay, that position is not reducing. Okay? Why is it not reducing?
Because you can't take away any hydrogens?
I didn't necessarily have hydrogens for this one. Okay? And some of this is actually going to come from, I goofed on the description here. So let's backtrack over to our ribose. Okay? And I said we had that blue OH float off. Technically, not really. Okay? When we're looking at the acetal and reversing the acetal, it would kick off the alcohol. That's not an alcohol. That would be kicking off water. When I deleted the bond there, what replaced that bond? Okay, those electrons all went with the oxygen, which means that carbon would be missing electrons. What stabilizes that carbon?
Your acid.
An acid would be H+. That carbon is positive. What would I need to stabilize a positive carbon?
Negative.
Electrons. If we take a look at that OH, what does that OH happen to have? Electrons. It is because of the presence of that OH that I have my reducing position. That's my carbonyl. If we go back and look at the glucose one that I've pointed to, do I have the OH to make the carbonyl? No. I would have the two alcohols. To get that carbon to react in a reducing type fashion, I would need to add water to the structure. I don't have that water, which means can't reduce it. Okay? So if you're in that full acetal position, you can't reduce. Okay? So the hemiacetal can be reduced, the hydrate can be reduced. Okay, so this is a classification for carbohydrates. You can hear things referenced as reducing or non-reducing. Okay? So, carbohydrates. Speaking of carbohydrates, when we look at those, in an OChem fashion, it's this nice zigzag chain with wedges and dashes and all sorts of fun stuff. We would have to go through and assign chirality to each of those positions, R and S, all the way down that. How many of you would like to do that? Okay, no. Okay, so Fischer ultimately went through and said the same thing. There's tons of possible carbohydrates out there. He wanted to invent a system that would allow him to classify those quickly and easily. If you're looking for this slide, I added it in, sorry. So it's not there. So Fischer drew what's on the right-hand side. Okay. Notice no wedges and dashes. But his format allowed him to assign R and S very, very quickly. For instance, the top one, I gotta check. That would be counterclockwise. Wow, that was pretty fast. Anybody notice a pattern? What does R mean? Clockwise. So if we start at noon and we go clockwise, we're going to the right. Okay. S is
Sinister.
sinister, referencing
Left-handedness.
biblical left-handedness. Okay. So if we go S, counterclockwise is going to the S or the left-hand direction. If we go through and look at this, OH versus H. Well, isn't OH higher priority? Yeah, and that would be on the right-hand side, but notice I made it S. We look at the next one. Where's the OH? Left-hand side. And which one's that? R. OH? Right. Signed it. Fischer allows us to assign very quickly R and S, just being the opposite of what we would initially have said. Okay? And so it allows us to assign those R's and S's very quickly, as opposed to over here, we'd have to change all of our orientations to align and match that fun little diagram thing that we all loved in Unit 1. Okay? The problem with this, though, is you have to be able to get from this zigzag formation to this nice straight chain, sometimes known as bow tie format. Okay? The bow tie isn't obvious, so let's go ahead and see where the bow tie is coming from. First, our rules. We have to orient the carbon chain on the vertical axis, okay? And all of the carbons must always be aimed away from you. Okay, so if we go through and look at the chain that I drew initially, they aren't all drawn away from you. They're actually in the plane of the paper. So I need to turn the molecule. But as soon as I turn it, are they all aimed away from you?
No.
It's a zigzag. It's going to zig out towards you, back away, out towards you, back away. So I would need to go through and change that orientation to ensure that I have those all aimed away. Those have to be all dashes. That first carbon is locked down perfect. What does it look like is right next to it?
Hydrogen and then
What's that shape look like?
bow tie.
Okay. There's the bow tie reference. Okay. That's what they're referencing, is the wedges coming at you. Okay. So, and stop making fun of my drawing. So the first one is fine. We'd move to the next one. It's aimed incorrectly, so I would have to do a rotation. So we could rotate the structure to get that to align. So we would go through and do that with the entire backbone until we achieved Fischer's orientation. Now that we're officially aligned, according to this, highest priority up top, constituents aimed towards you, as long as I know I've drawn a Fischer projection, I don't need wedges and dashes because
You know the long.
I know it's a Fischer projection. It's inherent in the system. So now I can delete the wedges and dashes and look. It aligns perfectly. Okay? The one thing I'll point out, just because I'm irritated about it, does that bother anybody else right there? That should be causing you to cringe a little bit, right?
The biologist, you're going to go easy on me.
Right? It really doesn't bother anybody else.
That's a little.
Not at all, man.
Low expectations.
You're showing a bond between a hydrogen and a carbon.
It's fine. It's fine.
And a hydrogen and a
That's horrible. You don't do that.
Why are you saying it was bothering you?
You just burned them.
Whatever. Okay? So let's go back now and say, well, we've oriented the molecule and flipped it all around so that it gets to this nice, beautiful fashion so we can simplify and draw a Fischer projection and all that's fine. Let's go back and look at what happened to our actual structure when we orient it in that way. And for those of you having a hard time recognizing that, I did attempt to show some three-dimensionality here. Notice that that is much larger than that font.
Yes.
Why?
Because it's closer.
It's further
curly
It's
cube.
closer towards you. This spirals, okay? And in this case, it's spiraling backwards away from you, starting with the carbonyl, okay? What would happen if, say, this oxygen attacked there? What do we end up with? 1, 2, 3, 4, 5, 6. We just made
6-member ring.
a 6. Oh my gosh.
Beautiful.
A 6-member ring, we just made glucose in the upper left-hand corner. So when you think about all the cyclic structures, those are kind of naturally falling out of how Fischer did his projection. He took a three-dimensional model that cyclized and just started rotating it until he came up with a drawing that he could then pretend worked. Right? That's where we end up with Fischer. Okay? Are you responsible for Fischer projections? Because I've gotten this question a couple times already. Yes. Fischer projections are just a three-dimensional manipulation of a molecule, just like single bond rotations, double bond lack of double bond rotations, Newman projections, chairs, Hayworth projections. All of those are different ways to represent a molecule. You are responsible for knowing how to represent all of the molecules. Okay? Does that mean you're going to see Fischer projections a lot? No. In fact, we barely talked about them. Okay? When will you see them?
Biochems?
In a biochemistry class. Okay? If you don't have to take biochem, don't stress a whole lot about it. We will see them in this class. We just won't see them that much. Okay. So why should we use acetals? Okay. Well, as we discussed, doing the actual acetal isn't particularly stable, just like the hydrates. Okay. Those aren't stable conformations. Okay. We have to have either super reactive carbonyls, which we typically don't, okay, because they aren't big enough to do anything with. Okay. Or we have to have very special conditions to establish them to work. One of those special conditions is that we form cyclic acetals. A cyclic acetal is something that works. Where does that show up? Carbohydrates, which we just talked about. So you see that in biochem. Where does it show up in a classical organic synthesis class? Okay. What did we do to the carbonyl functionality by turning it into an acetal? It's no longer there. I no longer see a carbonyl. Right? So if we change the structure, say, I don't know, drew in a double bond, and I wanted to reduce that pi bond, I could add hydrogen and platinum, as we talked about a while ago. But if I add hydrogen and platinum, that reacts with all pi bonds, including the carbonyl. But I don't want to reduce the carbonyl. I only want to reduce the alkene. Okay? One way we used to do that was to use an acetal. And we would first take that structure, convert it into the acetal form. Then I would react it with hydrogen and palladium or platinum to do the reduction.
And then reverse.
And then I would reverse the acetal, because the acetal is very easily reversed. The result is that I've kept the carbonyl functionality while I still did some other chemistry. Right? This is what's known as a protecting group. We've protected the carbonyl from reacting. Okay? It is usually frowned upon and is getting increasingly frowned upon as general or as chemistry goes for synthesis. Why? Well, my whole goal was just to add hydrogen to the alkene. To do that, I had to do 3 steps. All I wanted to do was one thing, and yet I had to do 3 things. I've tripled the workload. That means if I'm now paying somebody, I'm paying them to do a whole bunch of work that goes absolutely nowhere. That's expensive. Okay? That's green chemistry. Okay? At its heart, that's the core of what green chemistry is. But if we package it as I'm a money-grubbing jerk and I want to pay people as small amount as possible, nobody accepts it. Okay? So instead, we package it as green chemistry. By doing 1 reaction instead of 3, it's now not about money, it's about efficiency.
Save your materials.
Save your materials. It's still kind of money-grubbing.
Safety.
Safety. That person that's doing those reactions now isn't as exposed to as much chemicals because they only did 1 reaction instead of 3. Okay? So I'm looking out for my workers. Okay? I'm also looking out for the rest of the world because now I'm not producing a bunch of chemical waste. All of that is true, but that's not what's driving green chemistry. Okay? So, protecting groups, acetal super, super common, becoming less and less so. because green chemistry says don't do a bunch of reactions if you don't have to. Okay? Be more efficient with your process. So what would that process mean? If I want to get from this, or if I want this compound, the one with just the ketone, the cyclohexanone, maybe I shouldn't be starting with one that has an alkene on it. I should pick different starting materials or find different chemicals that allow me to do that conversion. Okay? So what green chemistry is about is think smarter about your reactions instead of just sledgehammering your way through them. Protecting groups is sledgehammering. Kind of makes sense? That was a lot of analogies in like 5 minutes. Okay. Okay. Nitriles. Carbon-nitrogen triple bond is also a polar pi bond. Okay? And as such, can react with our nucleophiles. Okay? We saw it react with our Grignards. We can also do it with water. Water can come in and attack. We break the polar pi bond, neutralize charges, and we would end with the amide. Okay? If we don't like that version with the ring, we can show it down here, and we end with the amide. What do both of these reactions also seem to be showing? What's the giant parentheses?
Acid base.
It forms a chain?
Is it forming a chain in the parentheses?
I was just guessing.
No, it keeps
So
reacting.
parentheses, if we're talking about polymers, yeah, that would make sense, but those aren't being drawn through bonds. We're actually saying that if we take H2O and H plus with the amide, it would continue to this. What did I start with or react to get the amide? The nitrile and H2O and H plus. What does this one say? Why are they putting it in parentheses? The reaction can continue to go. And in fact, it does continue to go. We don't stop at the amide. If we take a nitrile and add water and H+, we actually go all the way to the carboxylic acid in both these cases. Why is Cardi putting those in parentheses?
Is there a different mechanistic step?
They're a different mechanism. They're a nucleophilic addition followed by an elimination. What chapters are we talking about mechanistically? Nucleophilic addition. That chemistry is addressed in chapters 20 and 21. Okay? And because of that, Cardi's trying to say, don't look at that yet. We will see it, but that chemistry you're not responsible for yet. That's very bizarre in my opinion, but that's the point of those parentheticals. The reaction will continue on. We can't stop it at the amide, okay, with these reagents. Okay? If we break down and take a look at the acid hydrolyze mechanism to the amide again, presence of acid, the most reactive thing is H+. What needs to neutralize an H+?
Electrons.
Electrons. So where do we find electrons?
Lone pair.
Lone pair on the nitrogen. Kind of like what we did to our carbonyl oxygen, right? We protonated that to help it react. Nitrogen doesn't want to be positive, so what does it do? Steals electrons from the carbon, but now the carbon becomes positive. Now water can attack. Okay? This mechanism should look insanely familiar because this is the mechanism that we did for the hydrate. It is the mechanism that we did for the acetal. It's the exact same. Okay? You're just following those charge states through a reaction. Okay? We could do it as base hydrolysis. You'll notice it switches up this time. If we're under base hydrolysis, what charge do we see in solution? Negative. What species are negative? Bases is a fair answer. Try again. Nucleophiles. So in this case, instead of us affecting the electrophile, we've now made a stronger nucleophile. What does that nucleophile now do? Now I have to neutralize the nucleophile first. It's still going to react at the electrophilic carbon. Why is that carbon positive? There's a resonance effect with the nitrogen. Why is the resonance showing the electrons going towards the nitrogen? Nitrogen is more electronegative than the carbon. What you're establishing is differences in charge based off of electronegativity and just moving them accordingly. Identify the most reactive thing, react it. Continue on to the next step. Yes?
Those are the most reactive thing as the OH minus.
And what did the OH minus do in the very first step?
Attack.
It attacked. So,
So we're only determining where it is. Okay.
yeah. So the question becomes, where does it neutralize? Yes, the OH minus is the most reactive thing. How do I fix it? I have to find some place to fix. Okay? So it is very carefully addressing those differences in charge. Those differences in charge come from electronegativities. We're identifying polar bonds. The entire semester has been this. Okay? So now let's switch it up. Instead of looking at oxygen, this is a little bit weird. Let's take a look at nitrogen. So what's our difference between oxygen and nitrogen? Nitrogen is less electronegative. Yes.
Prefers three bonds.
Okay, nitrogen has 3 bonds instead of 2 for a neutral state.
It defaults to a single lone pair.
1 lone pair versus 2. Of those, where's our biggest difference? Our most important and relevant difference?
The lone pairs. Electronegativity.
The electronegativity. If nitrogen is less electronegative than oxygen, how is that going to define its chemistry?
It's more reactive.
That's right.
It's going to make less polar pi bonds.
Okay. So first, before we start addressing the reactivity, maybe you should frame it. What reactivity are you talking about? Okay. So the suggestion is we should look at it as a nucleophile. Why should we look at it as a nucleophile? There are lone pair electrons. There's a source of electrons. Yes, we should be looking at it as a nucleophile because there's freaking electrons there. Those act as nucleophiles. Okay? So now we should evaluate. Should it be more or less nucleophilic?
Nitrogen or oxygen?
Yeah.
More
Okay.
nucleophilic.
Which is more nucleophilic? Let's try that.
And nitrogen.
Does anyone want to disagree? You don't have to. Okay. Why should the nitrogen be more nucleophilic?
It's less electronegative.
By being less electronegative, what is it doing with its electrons?
It doesn't hold
It is
tight.
easier for the nitrogen to share them, which means the nitrogen becomes a stronger nucleophile than the oxygen. Okay. Is this going to change our reactions? Yeah, pretty significantly. Okay? And a lot of that hinges back on nitrogen's larger reactivity because it is less electronegative. It's more willing to donate those electrons outwards. Which means when we run a reaction, what am I more likely to see a charge on nitrogen become?
More positive.
It's going to be more positive more often than oxygen. Where we had positive oxygens, we might be screaming, no, don't do that. Nitrogen, we're like, yeah, don't do that. Like, it depends on the conditions. Nitrogen becomes a lot trickier to deal with because now you have to really think about the reagent conditions under which you're running. Okay? Oxygen was a little bit more cut and dry. Okay? So, don't worry about working out a mechanism together. We'll talk through it. So let's go ahead and take a look at the reaction shown below. There's 2 reactions there. Okay? The first one is our acetal mechanism. Okay? In the acetal, the big thing to note is that we had 2 oxygens come in and attack, right? 2 oxygens attacked. We good? Okay. Let's take a look at the nitrogen one. How many nitrogens came in and attacked? Why would I only get 1 nitrogen attack? Isn't nitrogen supposed to act just like oxygen? Shouldn't I be forming an acetal equivalent with 2 nitrogens?
No.
Why not?
Because nitrogen is electronegative. It's not going to just kick everything off the same way.
Nope.
Who won picks?
I don't know where you're going with that, so keep going.
Alright, so kind of valency a little bit. It's just the amount of bonds it could make. So at that point, nitrogen is full, whereas oxygen.
Okay, I could accept that. If we try to draw out the acetal in a similar fashion to our nitrogen, would that have been a happy structure?
No.
Why not?
Your oxygen has a positive charge.
The oxygen would have a positive charge. So if we consider nitrogen's ability to form bonds, nitrogen can be happy with 3 bonds, whereas oxygen, not so much. If we take a look here, our nitrogen has those 3 bonds. Why else? Okay, so this structure does happen. Okay, our acetal one. Okay, that green structure, that definitely does happen. But it's not happy, so what happens at that point?
It's going to leave.
How many oxygens have attacked so far? Just 1. What happens?
Another one.
The other one comes in and attacks to get us to the acetal. Why do I not need another nitrogen to come in and attack?
Because you stabilize nitrogen.
The nitrogen isn't charged. Why is the nitrogen not charged? 1 was referencing its bonds. It could have 3 bonds. Why is it allowed to have 3 bonds and oxygen only with 2? Really hand-wavy, but we're going to run with it.
Oxygen has 6 electrons.
Why does oxygen have more electrons than nitrogen?
It has more protons than nitrogen.
Okay, could be referencing the more protons. We don't evaluate protons in OChem, right? So what do we evaluate? Why does oxygen want more electrons than nitrogen?
More electronegative.
Oxygen was more electronegative than the nitrogen. It's not happy with that positive charge, so what's it going to do? Steal the electrons back. Nitrogen, on the other hand, doesn't need to have all of those electrons around it and is willing to share them. By willing to sharing them, what is that nitrogen doing a better job of?
Cooperating.
Sort of. Cooperating by doing what?
Sharing.
Sharing what?
Electrons.
Nitrogen was better at sharing electrons. What's the O? Nitrogen is
That's
a better nucleophile, which is what we concluded on the other side. Because nitrogen is a better nucleophile, I can go directly to this double bond state. The nitrogen can fully replace the oxygen. How does it go through and do it? Well, it's a very similar mechanism. Our lone pair on the nitrogen attacks the carbonyl. We break the pi bond. What's our result? We'd have a positive nitrogen and we'd have
Negative oxygen.
a negative oxygen. Are either of those happy?
Not particularly.
What could happen?
Stuff.
Stuff. Elaborate.
Oh, no, I don't want to.
The oxygen could share with the carbon, share
Why would it?
electrons.
Why would it do that?
The oxygen could share electrons downward, which means the carbon would exceed its octet. It would have to kick out a leaving group. What's our leaving group?
The nitrogen.
The nitrogen. We just talked about this being now an equilibrium reaction. This is reversible. Yes, that is incredibly important and unfortunate because that now means we have to worry about that. Thanks, Alex.
Yeah, thanks.
What could happen? What do you got?
You've got an acid and a base on the structure.
We have an acid and a base in that structure. So what could we do?
Protonate the oxygen and deprotonate the
Right.
nitrogen.
I would need to get a hydrogen from somewhere, right?
DH plus if you have a solution.
Okay. We could reference it as an H plus from solution. Where in the starting material do you see H plus?
Oh, never mind. I see H plus on the nitrogen now.
Okay. There is acidic hydrogens floating around. Once the nitrogen attacked, we do have acidic hydrogens. So we could show those. I would argue that that's too much of a pain to draw out, and I would just show it as H-B. Okay. I don't care where that hydrogen's coming from, but I do know that it is remotely acidic.
Well, they could bump into each other, right? Doesn't have to
It could
by
bump
itself.
into each other, and that's absolutely fair game. The problem with bumping into each other is that means I would have to draw two of these very large structures. How many of you have drawn one so far?
Not I.
Yeah. That's why we don't draw two. Mild guilt trip there. Just a little bit.
Are you
Okay.
judging us, Mike?
That is an acid-base reaction, and what could acid-base reactions do?
Reverse.
They could reverse. Thanks again, Alex, for the reversibility. You're on fire. We still have that positive hydrogen. What could we do? How do I stabilize that nitrogen? I would need to deprotonate it, which would mean I would need some form of a base. Okay. Note, that base, is it strong?
No,
How do you know that?
because it's not charged.
I'm not showing it charged. Why not?
Because you didn't feel like it.
Take a look at your starting materials. Do we see a strong base?
No.
No, that's why I don't use a strong base. I'm using something that has electrons. There's plenty of things that have electrons in there. I don't want to get uber specific on it because if I start to go over specific, I can run into mechanistic complications by showing things that don't exist. That's problematic. Okay? Now what happens? What we've approximated here is roughly the hemiacetal. What do we know needs to happen?
Oxygen needs to go away.
Oxygen needs to leave. How does oxygen leave? It could take electrons, right? But then it would leave as hydroxide. That's not a particularly stable leaving group, right? We don't like doing that. Is it leaving into a hydroxide-rich environment?
No.
No. So, guessing not?
No, not
Let's take a look at our starting materials.
Ah! It's not.
Okay. It's not. Okay. So, that's not a great leaving group.
You gotta make
Okay.
it into water.
We'd have to make it into a water, but to protonate it, what would I need? I would need an acid. What do you think the next question is going to be?
HB?
Do I have a strong acid?
No.
No. So we run into kind of a dilemma here on how do I potentially move through this. We know it needs to happen. Okay? So what we could go through and show is a very hand-wavy, nasty way of showing this, that those electrons, notice where they're coming from, the sigma bond, go out and need to react with a hydrogen. That hydrogen needs to be connected to something. But again, I'm showing it as B because what I'm trying to show is some generic form. I don't know what it is, but it needs to get a hydrogen from somewhere. By doing so, what has now happened?
Your oxygen is positively charged.
The oxygen has left because I took the electrons from that sigma bond. The carbon is now positive. How do I stabilize that carbon?
Nitrogen. And the base you just used.
I can now throw in a base again because that nitrogen is now positive. That base can be used to do what? Remove the hydrogen Zippity doo-dah, what do we have? Our final answer. Okay? There is no need for a second equivalent of nitrogen to come in and stabilize because the structure is already stable. We've done a whole bunch of acid-base steps to initiate or allow for the nucleophilic addition. And we encountered several that are problematic. Okay? Because we have to have those protonation acid-base concentrations. We encountered this exact same issue in the past. Okay? Remember the Acetal video, it had you go through and show the hydrate. And we said with the hydrate, it doesn't happen with just water. We had to do what? Add an acid or base catalyst to speed the process along. We have to do the same thing for our amines. Okay? We need some kind of acid catalyst. The extra thing that's fun with this, just like with the acetal, it is reversible. This product formation here is also heavily reversible. Okay? So we're going to clean this all up. Can I clean it all up? Cool. How do I reverse that reaction?
Add water.
I add water. So if I want to form the double bond to nitrogen, I need a crap ton of ammonia. If I want to go to the carbonyl, I need a crap ton of water. Okay? And that's going to help force it according to Le Chatelier's principle. Anybody else sick of saying double bond to nitrogen? I am, so I'm going to stop saying it. We're going to call it by its official name, which is an amine. Not amine, because amine is single bonds. As soon as we throw in a double bond, now it's an imine. Okay?
Thank goodness they chose such a vast distinction between the two names.
Oh, trust me, it gets worse. Okay? So, when we go through and do that, we've got our different catalyst issues that we can think about. Okay? What is the problem with acid catalyzing it? The point of the acid catalyst is to do what? Speed it up by doing what?
Protonate the oxygen.
By protonating the oxygen so that I get a better electrophile. Why is that problematic, David?
Because you've got two things that can pick up. You've got either a positive nitrogen or a positive oxygen, which is more stable.
We have two choices of electrons. We can pull from the oxygen or the nitrogen to share with that hydrogen. Which one is more willing to share with the hydrogen? The nitrogen. As soon as we add an acid catalyst, what does it do?
It stops being a
It
nucleophile.
kills the nucleophile right out of the gate. Okay, yay, nitrogens. Does it still work? Yes. Fudge. Okay? It works even though we kill some of the nucleophile. Okay? We still get some of the electrophile to be protonated. Some of the remaining nucleophile can attack, and it still progresses forwards. Okay? Why? Le Chatelier or Alex, whoever you want to blame. Okay? We've added enough excess of this nitrogen to push the reaction to the imine. The acid is there and it's going to mess with the reaction. It's also going to help the reaction in a lot of those cases. Okay? We could try and run it under base conditions. How do I get it to be base conditions? What's the problem with chucking in an OH?
Can act as a nucleophile.
It'll act as a nucleophile. Is OH strong enough to deprotonate the NH3?
Yes.
No.
Oh, yeah.
So adding sodium hydroxide, all it does is it adds another nucleophile that could potentially react in this. It doesn't actually deprotonate and activate the nitrogen. Okay? So we have to be very careful with running it under base conditions. Okay? The extra problem with running it under base conditions does that look familiar? Anybody?
Yeah.
What does that look familiar? What does that remind you of?
The NH3 we were using.
What can you tell me about the alpha hydrogen?
It's gonna get slow.
It's acidic.
It's gonna
Gonna get swooped when nitrogen comes in with its troops.
The nitrogen comes in and will deprotonate, creating a carbon nucleophile. The nitrogen doesn't act as a nucleophile. Okay? So when we're running through with our nitrogen, we can get all sorts of nasty side reactions that push and diminish our yield. Okay? The acidic conditions are better for running the nucleophilic additions because as soon as I make the nitrogen more nucleophilic, it becomes so much more nucleophilic that it prefers to act as a base, in which case I get an acid-base reaction, not a nucleophile addition reaction. Okay? Kind of makes sense? So, nitrogens are fun and exceedingly frustrating at the same time. Okay? So, go ahead and take a look at these structures, see what you can come up with. I'm not giving you 10 minutes, but I'll give you some time to take a look at them.
be right.
Okay, so let's go ahead and take a look. We're going to double back here real quickly. In the course of this reaction, what changed? In fact, it's a little bit better if we go all the way back.
You replace oxygen with nitrogen.
Okay, because that equation isn't balanced, right? What else is produced?
H2.
H2O. Oxygen, and we remove 2 hydrogens. What happened with the last hydrogen?
It stayed.
Nothing. It stayed behind. So when we're reacting this, remember we said to reverse the reaction, we had to add a bunch of water. Why do we have to add a bunch of water?
To put them back.
To put those pieces back. Okay? So if you're going to go through and react a nitrogen with a carbonyl, delete H2O from those pieces. Okay? So let's go ahead and take a look at the first reaction. For sure, there's the oxygen. Where's my H2?
On the nitrogen.
On the nitrogen.
We all laughed really bad.
What happened to the bond between the carbon and the nitrogen?
It stayed.
Nothing. It's still there.
Is that the enamine?
No, this is still imine. Okay. The question that I asked a bunch of you is which would nitrogen rather take electrons from, hydrogen or carbon? Rather going to take it from hydrogen because?
Electron.
Which would nitrogen rather take electrons from, hydrogen or carbon?
Hydrogen.
Hydrogen doesn't have it.
Is it because hydrogen?
Let's draw out our structure. Here's our nitrogen, CH3, H. In the very first attack, what happens? These electrons attack. What charge does our nitrogen become? Positive. What does it need? Electrons. Where does it get the electrons?
The hydrogen.
From the hydrogen.
I was thinking you were meaning.
Is it,
Okay.
Is it because hydrogen's less electronegative?
Hydrogen is less electronegative than the carbon. That's why it takes the electrons from the hydrogen, not from the carbon. When you push through, that's what you end with. What happens in the next one?
Same kind of process.
The same kind of process. Double bond to the nitrogen, right? Where did it get electrons from?
Hydrogen.
From the hydrogens, which means
The OH is still attached.
the OH is still attached. That oxygen, those 2 hydrogens. Okay. What happens in the next one? That one's weird. I'll absolutely grant you that.
Do you get a single bond between the nitrogen and the carbon?
If we went through and did that, what would be the problem?
It's wrong.
All the carbons.
The nitrogen is positive. And in the past cases, what happened?
It was neutral.
What happened when we formed the positive nitrogen?
It needed electrons.
We deprotonated. We removed electrons from a hydrogen. Do we have a hydrogen connected to that nitrogen? No.
It's
So we might be like, well, there's no hydrogens to remove. That's unstable. That can't form.
It gets them from the double bond.
Or is there an H2 over? Oh, no, it's hydrogen. Oh. Ew.
And for those of you being like, oh my God, that is so ugly. I've never in my life seen that before. It's called
Elimination.
this would be what functional group?
Alkene,
An alkene. The nitrogen is
amine.
an amine. There's an amine. You're like, I've never before in my life seen that. That is a load of crap. We've never talked about that before. What was that?
Yeah, what was
You're on a roll there, Alex. You're just pissing everybody off.
Yeah, right.
Enol.
It's an enol. What we have gone through is effectively a keto-enol tautomerization, except instead of it being an oxygen, it is a nitrogen. And it turns out nitrogen is more willing to do that than the oxygen. Why? It has to do with its nucleophilicity and its ability to stabilize those charges better. So we end up seeing a large formation of the enamine. So much so that we see the enamine show up in a lot of reactions. Lab. Okay. Last one. What's that question mark?
What did we put on there?
What did we attach? And?
NH2.
Okay. We then add a strong base. Sodium hydroxide. What does that sodium hydroxide attack?
The NH2.
It attacks the NH2 and it removes 2 hydrogens. Right? That would make that nitrogen incredibly negative. So what does it do?
Share.
Shares electrons inwards.
You get a nitrile.
That would then exceed the octet on that nitrogen. So it kicks electrons out to our water. Fun little results on this one. Cyclohexane. Complete removal and loss of that carbonyl. That is known as the Wolff-Kitchener reduction. Okay, neat little reduction. What happened to those nitrogens?
Nitrogen gas, or they return to what they were earlier?
They bubble out as nitrogen gas, which is what drives that reaction. We'll look at that mechanism in a little bit more detail when we move into chapter 19. Okay. There's the Wolff-Kitchener reduction. I would give you a mechanism, but the last time I did that mechanism, it covered the entire screen because it's something like 16 steps. Most of it are just acid-base steps. Okay? You're following the same basic pattern all the way through. You just repeat it a whole bunch. This shows a big old summary of all of the reactions with our carbonyl section, which is really getting us to the aldol. I really want to talk through this one. We've already seen some of this. We throw a strong base at a carbonyl compound. We have an acidic hydrogen. It deprotonates. That gives us a nucleophile. Because we used a not stupidly strong base, not only do I have that nucleophile, I also have that electrophile floating around. So what can happen? Those two can react with each other. Okay? That'll go through a sequence of steps which you should be able to walk your way through mechanistically. Okay? And you would end at that structure. What functional groups are in that structure? An aldehyde and an alcohol, also known as an aldol. Okay? The aldol is not a particularly stable structure thermodynamically, and it easily reverts back to the carbonyl. Give it just a little bit of heat, though, and you can do an elimination reaction. This product is much more thermodynamically stable because we have conjugation of the pi system. That is now an aldol followed by a condensation reaction, typically known as. This was an aldehyde and an alcohol. What did we call it? An aldol. This is the aldol followed by a condensation. Aldol condensation. That's it. Okay. Typically, when we talk about aldol reactions, we refer to them as aldol condensations. We almost always do the elimination. Okay. It is rare to not see the elimination on there. Okay. We will pick up there. I'll walk through that mechanism in a little bit more detail on Wednesday. And then what we will do is very quickly jump straight into practice. I'll give you 10 minutes. Okay? So, with that, we'll go ahead and stop.